So at the start of this unit, we said we were going to consider two fundamental laws, Coulomb's law, which we've already looked at, and Gauss's law. And so in order to start describing Gauss's law, we actually have to define something new, which is called electric flux density. And so the reason we need to define this electric flux density is our electric field, the intensity of that is going to depend on the medium in which the field exists. And in some cases, we're going to need something that represents the field but is independent of the medium. And so in order to do that, we're going to define our electric flux density as d, which is also a vector quantity, which is just epsilon naught times the electric field. And right now we're just going to leave that as epsilon naught. We're going to come back in the next unit and we're going to adjust this equation a little bit to be more general. But if we're considering a vacuum, then this equation is good. So again, this d is going to be independent of the medium. So independent of our medium. And so this is our electric flux density. And so the units for our electric flux density are going to be coulombs per meter squared. So now that we have this electric flux density, we can define electric flux that is going through a surface. So our electric flux is going to be psi, which is equal to the integral over the surface of d dot ds. So the same form of our surface integrals that we looked at earlier. So this is what we're going to define as our electric flux. Now, with this relatively simple relationship between our d and e, we can easily get our electric flux density for structures that we already know the electric field for. So let's just say we can find d very easily when E is known. So for example, we looked at our infinite line charge. So for an infinite line charge then, we could just say that our D, our electric flux density, is equal to, so we still have rho L in the numerator, and now our denominator is going to be the same. We're just going to exclude the epsilon naught term because it basically cancels out with this epsilon naught here that we multiply by our E. So we have 2 pi rho in our rho direction. And so we could compare that to the previous equation we had for our electric field due to an infinite line charge, which is on page 4-12 in the notes. So we don't necessarily have to already have our E field equation. We can also go back to the general equation. So we can go back to our general equations. And so remember we had a general equation for line charge, for surface charge, and for volume charge. So for example, let's say we wanted to know our electric flux density due to some volume charge. Well, that's just going to be from the general equation, the integral over the volume of rho v dv. And in our denominator now, we just don't have that epsilon term is the only difference. So we have 4 pi r squared in the r direction. So again, the only difference is we've dropped that epsilon naught term in the denominator. And so you can compare that to page 4-9 to see the general form for our electric field. So if you want to get some extra practice sort of finding this D, which really it's kind of the same thing as finding E, you can look at example 4.7, which is on page 131. And so this is a good example to look at because not only are you getting practice finding D, but we're also getting practice with that superposition. So we have multiple charge distributions. So there's actually a point charge and an infinite line. So both relatively easy to deal with, and we just remember add each of those contributions to get the total contribution. Unfortunately, we have a lot to cover, so we're not going to have time to go through that, but definitely take a look, and if you run into any issues or have questions, let me know.